Hello and welcome back to your Chem 4 lecture. We are moving on into chapter 15 this week, which is all about lipids. So we are firmly entering the biochemistry portion of the class that we're going to finish up with here. And the first set of molecules that we'll talk about, I guess after carbohydrates, which we kind of snuck in there in the organic part, we're going to talk about lipids next. And there are two types of lipids, and we'll show you this on the next slide here. There's two main types. There are those that have fatty acids and those that have a steroid nucleus. So these are kind of not closely related to one another necessarily, other than the fact that they are very nonpolar. So these are going to contain a lot of carbon-carbon and carbon-hydrogen bonds. And so the lipids are going to represent basically the nonpolar part of our biological systems. So we'll talk about it in that context. Now, because they're nonpolar, that means that they're soluble in organic solvents, but they will not be soluble in water. Lipids are commonly known as fats, and that's actually where the name lipid comes from the Greek word lipos. Okay, and we'll talk about all of this here in the near future. Here we go. So we mentioned already that we have two different types. We have fatty acid types of lipids, and these include waxes, fats, oils, and phospholipids. These all have ester bonds that basically give fatty acids. And you ask yourself, what's a fatty acid? Well, what it is basically is it's a carboxylic acid with a very long tail. So like previously we were talking about like acetic acid or propanoic acid or butanoic acid. Those are relatively short carboxylic acids that are still soluble in water. But we know as we add more carbons and hydrogens to this thing, it's going to get more nonpolar. So it's going to be less soluble in water. And hence the name fatty acid basically is it's a carboxylic acid that is not soluble in water because it has this long nonpolar tail. Let's see here. So then we have steroids. So steroids is the other part. Steroids don't contain fatty acids. They can't be hydrolyzed. And what they are basically is what they have in common is basically they have a fused carbon ring structure here. So there's 4 carbon rings that are fused together. So it's a 6-membered ring with a 6-membered ring and another 6-membered ring, and then a 5-membered ring on the outside. And we'll see, we have a whole section here. There's a whole lecture on steroids where these have different substituents that kind of distinguish them. We will talk about that in the future. But two very clearly different types here of lipids. So now within those subtypes, we have steroids, which stays pretty much as steroids. Again, it's a weird structure, but because it's nonpolar, we throw it in with the other lipids. Fatty acids actually produce waxes, they produce triacylglycerols, glycerophospholipids, and sphingolipids. So the phospholipid classes here. And again, these are naturally occurring. They are soluble in organic solvents, but they're not soluble in water. So if we want to look at the general structure of lipids, the reason that we have these 4 classified as fatty acids is that they contain a fatty acid in their final structure. Waxes, for example, and we'll talk about this more in depth, is they have a long chain alcohol that's got an ester bond to the fatty acid. Triacylglycerols, these have a glycerol component, which is a 3-trialcohol compound that's esterified 3 separate times to 3 different fatty acids. Glycerophospholipids are similar, where they have that same trialcohol glycerol that we'll show soon, where it's now, it is bonded to 2 fatty acids and then 1 phosphate and amino alcohol structure. And then finally, sphingolipids, which have a somewhat similar structure to glycerophospholipids, but they only have 1 fatty acid, and you have this sphingosine back. We'll talk more about that again as we go on. Okay, so here we go. Sample exercise number 1. You can go ahead and get out your PDFs now. Lipids are characterized by the presence of fatty acids or a steroid nucleus. Which type is described by the following? A contains so this is your either fatty acid or steroid. A contains a fused 4-membered ring system. B contains long carbon chains, or C includes carbonyl. So go ahead. Each of these describes a different category between either fatty acids or a steroid nucleus. Tell me what it is, and we will come back with the answer in just a moment. Okay, let's go ahead and give it a shot. So the 4-membered ring system, fused 4-membered ring system is a steroid. That's easy enough, right? It's that little nucleus there for the steroid. That's what's going to make up the steroid compound. The long carbon chains and carbonyl groups, those are both fatty acids, right? The carbonyl group is the ester when it's bonded, or a carboxylic acid in the case of if you have the free fatty acid. Okay, how about this? Which of the following is not a characteristic of lipid, A through D? May contain a carboxylic acid group, may contain a 4-ring structure, soluble in water, or mostly non-polar. Go ahead, pause the video, come up with your answer, and we'll look at the answer here in just a moment. Okay, let's take a look. So of course, the one that is not is these are insoluble in water. So we don't want, we know that they're not soluble in water, so the correct answer is C. Okay, next up, fatty acids. So we're going to talk about fatty acids because there's a few different types. So fatty acids have basically long unbranched carbon chains, and they have a carboxylic acid group at the end. So it's just a straight chain. It's going to be 12 to 18 carbon atoms long. And because of this long carbon chain, that is, all carbon-carbon and carbon-hydrogen bonds, this is going to be insoluble in water, very non-polar. Now, there's two different types of fatty acids. We have saturated fatty acids and unsaturated fatty acids. Now, this should sound familiar because we already talked about saturation when we talked about hydrocarbons. And remember, saturated hydrocarbons have only single bonds. Unsaturated hydrocarbons have some double or triple bond structure. The same is true for fatty acids. Saturated fatty acids have only carbon-carbon single bonds. There's no double bonds or triple bonds. Fatty acids are unsaturated when they do have at least one double bond in the carbon chain. So now, how do you draw fatty acids? Well, the way that you can draw it basically is there's a bunch of different ways. Of course, the line angle formula still works just fine. This is lauric acid here, for example, and it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons in the chain. Again, I usually prefer to draw the line angle structure because you don't have to do so many CH2, CH2, CH2. You have a few different condensed options here. So for example, because you have 10 CH2s in a row, you can write it this way where you have a methyl group at the end, followed by CH2 10 times. So we put CH2 in parentheses with a subscript of 10, followed by a carboxylic acid. That's also a fine way to draw that. Okay, so for saturated fatty acids, this is how we kind of classify them here. So lauric acid, that's the one that we just looked at. Now, one of the important ratios here that we're going to see is for fatty acids. There's always a ratio given of carbon atoms to double bonds. So for lauric acid, it has no double bonds. So it has a ratio of 12 to 0 for carbon atoms to double bonds. And lauric acid has a melting point of 44, and it is present in coconut oil. That's the reason that coconut oil is a solid at room temperature, is because it contains a lot of lauric acid. Now, as we increase the number of carbons in the chain, so going to myristic, and then palmitic, and then stearic acid, these are all unsaturated, or I'm sorry, these are all saturated fats, 14 to 0 for myristic, 16 to 0 for palmitic, and 18 to 0 for stearic. As we increase the number of carbons with no double bonds, we increase the melting point of the compound. And this will be clear for reasons that we'll see in a minute. As we increase the number of carbon atoms and hydrogen atoms in the compound, we increase the molar mass. And so we're increasing the likelihood of having dispersion forces available to hold them together. So just pointing out here, all of these melting points are above room temperature. Coconut, palm oil, animal fat oil. I'm not sure about nutmeg. I just think of nutmeg the spice. I'm not sure what the relationship is here for myristic acid. But palm oil, if you're familiar, is also solid at room temperature. And of course, animal fats, things like butter or lard contain a lot of stearic acid, and those are also solids at room temperature. Okay, now, after we get the saturated fatty acids, then we can talk about the different types of unsaturated fatty acids. The first being monounsaturated fatty acids. Now, just like it sounds, monounsaturated fatty acids have just a single double carbon-carbon double bond. So for example, palmitoleic acid has 16 carbon atoms and just a single double bond. So its ratio is 16 to 1. And this is something that's present in butter, for example. the melting point of palmitoleic acid is 0. So it's basically a liquid at room temperature. So note, all of these that we had for the saturated fatty acids, all were solids at room temperature. And now that we're in these unsaturated fatty acids, we're finding that they're actually liquids at room temperature. Oleic acid is the same. It's present in olive oil, grapeseed oil as well. And these have at least one double bond. So oleic acid has 18 carbons and one double bond. So again, that's an 18-to-1 ratio. Again, we increase the number of carbons, we increase the melting point, but we're still below room temperature. So that's why you have olive oil as canola oil, etc., as liquids at room temperature. Butter is solid because it has a lot of saturated fats with it as well. Okay, now beyond that, of course, you have monounsaturated fatty acids. You can also imagine polyunsaturated fatty acids, where they have more than one double bond. So linoleic acid, for example, is present in soybean, safflower, and sunflower oil, and it's present in basically 2 double bonds to the 18 carbons that are there. And again, the melting point is very low. It's -5 degrees Celsius. So it's definitely a liquid at room temperature. It's even a liquid at freezing temperatures. Linolenic acid is present in corn. And here it is, I think it's 3 double bonds here, right? 1, 2, 3. This should actually be an 18-to-3 ratio. Apologize for that. So there should be, with 3 double bonds now, we increase the number of double bonds, that decreases the melting point. And then look at arachidonic acid. Arachidonic acid is really interesting fatty acid. That's actually really important for something that we'll talk about in a little bit. But it has 4 double bonds in it to the 20 carbons. And that means with that number of double bonds, melting point is even lower at -50 degrees Celsius. So that really wants to be a liquid. Okay, so beyond that, we also have to consider the fact that with these double bonds, we have to consider the stereochemistry of the double bonds. Remember, double bonds can be cis or they can be trans, right? Cis would be where both of the carbon groups are on the same side of the double bond, or it could be trans, where they're on opposite sides of the double bond. Naturally occurring unsaturated fatty acids have at least one cis double bond, almost all of them. So cis oleic acid is the way that oleic acid is found, in, I want to say olive oil, did I get it right? Olive oil, yes. Oleic acid is in olive oil, and it's always found in the cis form in the olive oil itself. Yeah, and so this is the case for these unsaturated fatty acids. The double bonds tend to be the cis structure rather than trans structure. Now, we have, and so this is something I guess it's not going to come up just yet. We might talk about this in the future. You may have heard of a type of fatty acid called the trans fatty acid. And this occurs when we take unsaturated fatty acids and try to saturate them. Sometimes rather than forming all single bonds, some of these double bonds switch from the cis to the trans isomers. And so when that happens, these trans fatty acids, they seem to have some negative consequences for our health. I think we talk about it later in this chapter, but just want to point out the cis, the natural version, those tend to be better for you rather than the trans fatty acids, which tend to lead to some health consequences. Okay, now let's bring up this concept of the essential fatty acid. Now you've heard of this before with like amino acids. There's amino acids and there's essential amino acids. Same thing with fatty acids. We'll talk more about amino acids in the next chapter, but for fatty acids, basically, as humans, we can synthesize some of the fatty acids that we need, either from carbohydrates or if we have, an intake of other fatty acids. But we can't actually synthesize the polyunsaturated fatty acids like linoleic and linolenic acid or arachidonic acid. So we have to actually obtain those from the diet. This is why they are known as essential fatty acids. In other words, they're essential to our diet in order to be healthy. Okay, now let's talk about some of the properties of these saturated fatty acids. Now, saturated fatty acids, because they only contain single carbon-carbon bonds, they fit close together in a regular pattern. basically there's a strong dispersion attractive force where these molecules are able to fit really close to one another because there's no branches in the chain, basically. They can lay right on top of one another, and they have a lot of dispersion forces that are able to be there. Because of that, that's why they have high melting points, and they're usually solids at room temperature. The way that you can think about this is, if you think about the saturated fatty acids, think of them like Pringles, right? Or whatever, stack of chips company that you prefer. I don't get paid by Pringles. So with a Pringles chip, you see that it lays flat exactly on top of the one below it, below it, below it, below it. And that's because it has a regular shape. Same thing with these saturated fatty acids. They have a regular shape, and so they're able to interact, at all points on the fatty acid, from the tail all the way to the head. On the other hand, these unsaturated fatty acids, like oleic acid, for example, they have these cis double bonds. Because of that, they're not able to really get close to one another. They can't lay on top of each other in the same regular fashion. They're going to be all jumbled up, just like we see here. And that would be like, for example, like a bag of like a normal chip, where you pour the chips out and they're just like barely touching each other in all sorts of weird angles. Because they don't have the same surface area contact that we have from the saturated fatty acids, that means they have lower amount of dispersion forces. Basically, there's fewer temporary dipoles and fewer induced dipoles holding them together. Okay, here, let's take a look at sample exercise number 3. Consider the condensed structural formula for oleic acid. Ask yourself the following. Why is this molecule an acid? How many total carbon atoms are in oleic acid? Is it saturated, monounsaturated, or polyunsaturated? Is it likely to be solid or liquid at room temperature? And would it be soluble in water? So go ahead, think about what we talked about, the difference between saturated and unsaturated fatty acids, and we'll look at the answer when we come back. So go ahead, pause the video, and we'll take a look when we come back. Okay, let's take a look. Okay, so first up, why is the molecule an acid? Well, it's got a carboxylic acid functional group. Because of that, that means that this hydrogen is weakly acidic. How many total carbon atoms are there? Well, okay, so we have 1 plus 7, so 8, 9, 10, 17, 18. So there should be 18 total carbon atoms. Is it saturated, monounsaturated, or polyunsaturated? Well, when we look at it, there's only a single double bond, so that's monounsaturated. Is it likely to be solid or liquid? Unsaturated fatty acids are liquids at room temperature. And then finally, would it be soluble in water? No, still insoluble in water because it has a long carbon chain that's nonpolar. Okay, great. So we're ready to talk about arachidonic acid and one of the really interesting health consequences of lipids, which is this prostaglandins. So prostaglandins are hormone-like substances that your cells produce. The other name for them is eicosanoids, and because these are formed from arachidonic acid, remember that arachidonic acid had 20 carbon atoms and 4 double bonds. And what it is basically is there's a 5-carbon ring, and it can differ based on the substituents that are bonded there. So that's kind of this prostaglandin thing that's going to be related to the arachidonic acid. Prostaglandins themselves are involved in a wide variety of functions, so they can lower or raise blood pressure, and they stimulate contraction or relaxation of the smooth muscle of the uterus. Also, when tissues get injured, arachidonic acid gets converted into prostaglandins, and that is responsible for the inflammation and pain response in the area. So like if you're trying to, you're trying to hang a poster or something like that, and you accidentally hit your thumb with your hammer, the arachidonic acid in the area where it's hit is going to be converted into a prostaglandin. And this leads into pain and inflammation. It could lead to fever, of course, but that's more like it's just going to get hot in the area. Now, if you take a non-steroidal anti-inflammatory drug, that's an NSAID. So aspirin is one of those. I believe ibuprofen is another one of those. That prevents the production of prostaglandins. So basically, it can reduce the pain and inflammation response. That's why for some injuries or some types of pain, you want to take an NSAID rather than like Tylenol, for example. That's why, there's a difference between ibuprofen and Tylenol. They have different activities, basically. Yeah, okay, right. So here's the ones that are NSAIDs. I hope I'm saying that right. It's not NSAIDs. I'm not sure, totally sure, but I've always said NSAIDs and no one's corrected me. So aspirin is one, ibuprofen is another, and then naproxen, which is in Aleve and naproxen. And then here we have another set down here. Ketoprofen and nabumetone are all NSAIDs that can decrease pain and inflammation. Okay, let's talk about another thing, how these fatty acids are linked to health. That's something you probably heard of. People always say you need to have fish oil in your diet because fish oils are good for you. So why is that? Well, the reason that we talk about fish oils a lot in terms of health is that they have a particular type of fatty acid called an omega-3 fatty acid. Now, we call it an omega-3. Well, okay, let's give you the other example here that we were talking about already. So vegetables have a different type of fatty acid called an omega-6 fatty acid. And what that means is that the first double bond occurs at carbon 6, counting from the back end. So think omega means end, right? So omega is the last letter in the Greek alphabet. So we're going to start from the end and we're going to count up 1, 2, 3, 4, 5, 6. That's where the first double bond is present for these omega-6 acids. Now, on the other hand, fish oils contain a lot of double bonds at carbon 3, counting from the methyl end. That's why we call it omega-3 fatty acids. So linolenic acid, icosapentaenoic acid, or EPA, and then docosahexaenoic acid, DHA. And these are all examples of omega-3. Again, we count from the methyl end of the chain, 1, 2, 3. That's the first double bond. It's an omega-3 fatty acid. So now, why is it that these are important? Well, cholesterol can form plaques that adhere to the walls of blood vessels. And we're going to see like pictures of what this looks like in the future because cholesterol is a steroid. So in the very near future, we'll see this here. Now, when it kind of narrows the blood vessels, that means that blood pressure has to be increased to move blood faster through that blood vessel. Then more plaque is going to form because a higher cholesterol. So there's blood clots that block blood vessels, and that can cause a heart attack. Omega-3 fatty acids lower the tendency of these blood platelets to stick together, and that reduces the possibility of these blood clots. So it can be really helpful in heart disease. Okay. All right. So go back through your notes. We've talked about a lot of different types of acids here. So remember, your notes are going to be eligible for the test. So you'll be able to use your notes on the test and label the following fatty acids as saturated, monounsaturated, or polyunsaturated. That's linolenic, palmitoleic, and stearic. So go ahead, pause the video, go back through your notes, and we'll take a look at the answer when we come back. So pause the video. Okay, we're back. So linolenic, remember that was polyunsaturated, palmitoleic was monounsaturated, and stearic was a saturated fatty acid. Okay, all right, that covers the introduction to this chapter. We're going to talk more about the different types of fatty acid compounds in the next lecture, and then we'll move on into steroids and I think cell membranes is the last one. Until then, I'll see you soon. Bye-bye.